So we ended last time talking about Poisson brackets and Poisson systems. And this is what I've got listed here is exactly a copy and paste from last time, just what I wrote at the end. So and there's some good references. The Poisson bracket and Poisson system approach, you could view it as an alternative way to write Hamilton's canonical equations. Those are the Q dot equals partial H, P dot equals negative partial H stuff that we've done, but that's just one kind of Hamiltonian system. So Poisson brackets can be used for those systems, but then they also kind of generalize the idea of Hamiltonian systems, preserving some of the properties that we've talked about that are very nice, to a much wider array of settings, which includes infinite dimensional systems. So not just finite dimensional rigid body and particle systems, but PDEs related to continuum mechanics. So that's what this thing on the right, this Venn diagram, we call this kind of larger extended set the Poisson systems, and a subset of that are the Hamilton's canonical equations, which is what we've basically talked about up till now. So what's this next part? This next part just kind of gives an idea of the fundamental thing in with the Poisson bracket approach is that you are looking at scalar functions f that are a function of your phase space coordinates. So Q, P, and then possibly time. And you want to know how a scalar function evolves along trajectories. And you might say, well, that seems pretty limiting, but it's not. Any of the individual coordinates like Qi could be a scalar function or some other thing that you want to calculate that's a function of Q's and P's. So we first write the total derivative, f dot, total derivative of f that's along trajectories. And then we're just writing the chain rule in this first step here. This is just chain rule. And then we collect and we write what Qi dot is and Pi dot is from Hamilton's canonical equations. And we just substitute in. And then we get this thing, this summation over partial derivatives that is kind of interesting. And so we define it as the Poisson bracket of f with h. Both f and h are just scalar functions of the phase space coordinates. So we've defined this thing. And if you do that, then it provides a really compact way to write how a scalar function evolves in time. So f dot equals this Poisson bracket of f with h plus a part that has to do with if f explicitly depended on time. So we, if you look at how we've defined this bracket thing, I mean, we'll get into what does that all mean. There's some symmetries there, but first, things get even easier if f doesn't depend on time. So now some new stuff. If my function f does not explicitly depend on time, then it means partial f partial t is 0. So this thing simplifies even further. We have f dot is just the bracket, Poisson bracket of f with h, which we interpret to be, okay, it's this collection of all these partial derivatives with respect to q and p and that minus sign and all that. So we have this, which is even simpler. Okay, so what about it? Well, so suppose I want to know how the variable Qi evolves, or let me say, sorry, Qj. I've got the index I for something else. So if f is Qj, then Qj dot would be, well, Qj as a function depends only on Qj, it doesn't depend on time. So we can use this simpler way of writing things. We've got the Poisson bracket of Qj with h. And if you look up above, well, if this depends only on j, then we're only going to pick out one of the terms of this partial derivative, or this sum over partial derivatives. So the only term that we pick up is partial h, partial pj. And well, that makes sense. If we did the same thing for if f is pj, we would find that pj dot is pj with h, and it would pick out another term. What would it be? It would come from this side over here, partial f, partial pj equaling 1, but we got that minus sign times partial h, partial qj. So this would give us minus partial h, partial qj. And so notice what this is. Qj dot equals partial h, partial pj. Pj dot is partial h minus partial h, partial qj. These are Hamilton's canonical equations. So this way of writing this Poisson bracket thing, at least there's some consistency there. It recovers Hamilton's canonical equations. Good. At this point, it's easier if we start using the X notation or the symplectic notation from before. So if you can recall that, I call it the X notation. Or some books just call it the symplectic notation. This is where we define a vector x, which is made up of all of the q's, so q1 through qn, and then all of the p's. And this canonical symplectic matrix will be important too, so let me just remind you what that is. It was this matrix 0, the n by n identity, negative n by n identity, and zeros. In this X notation, Poisson bracket of f with h equals the gradient of f transpose times j times the gradient of h, where the gradient of f, this is the gradient of f as with respect to x. So instead of writing f as a function of q and p, we just write it as f of x. And same with h. So h is a function of x, which is just the first n of them is the q's and the next n of them is the p's. So same here, partial h is partial h with respect to x. So if we write it this way, if we did gradient of f dotted with gradient of h, this would just be f transpose times, or gradient f transpose times gradient h. So this looks like some kind of funny dot product with, instead of there being an implied identity matrix there, we've got some other matrix. We've got the J matrix. So that's worth pointing out. This looks like a strange dot product of two gradients. Okay. And you might wonder, well, why are we just using h? You can, just given this strict mathematical definition of what the Poisson bracket is of two scalar functions, you could take the Poisson bracket of any two functions. So one could take the Poisson bracket, and sometimes I'll abbreviate this as PB. And if you remember, here's P, B, and J. It's a joke. Okay. One could take the Poisson bracket of any two functions. Let's call them U, Q, P, and T, and V, Q, P, and T. And we could equivalently just say this is a function of X and T, or this is a function of X and T. And the Poisson bracket operation, it is, so this will get us into an area called abstract algebra. The Poisson bracket operation defines a type of algebra. And we're used to the usual algebra. Okay, so let's delve into abstract algebra a little bit. You didn't know you were going to get into abstract algebra. Maybe you did. First, before talking about abstract algebra, what's the usual algebra? The usual algebra is like X is a real number, Y is a real number, and we have this well-known thing called multiplication of two numbers. Let's, X times Y. That's the usual algebra, and that also is going to be a real number. So the multiplication of real numbers is the, if you want, usual algebra. And this thing that's implied here, the operation is multiplication. And we all know some things about multiplication. We know that it doesn't matter the order. So X multiplied Y is the same as Y multiplying X. So that property is sometimes called symmetry. We also know some other stuff, but that kind of lays the groundwork. That's the usual algebra. The Poisson bracket is not the usual algebra. Well, first of all, it's not over the real numbers. It takes in, so where the usual algebra takes in two real numbers, multiplies them, and spits out another real number. The Poisson bracket takes in two scalar functions of phase space, spits out another scalar function of phase space. So the Poisson bracket operation is a type of algebra. You have to kind of expand your notion of what an algebra is. And they teach courses on abstract algebra in the math department. So it's a type of algebra called a, it's called a Lie algebra. Which the usual multiplication of real numbers algebra is not. That is not a Lie algebra. But what does it mean to be a Lie algebra? This means that the Poisson bracket has certain special properties. And we're talking mathematical properties. As an operation on two scalar functions. It yields another scalar function. Because we scalar function of phase space. And here are those properties. So these are the properties that any Lie algebra will obey. And I will show you an example of a Lie algebra that you're very familiar with after we go through the properties. So if I have a function U, I take the Lie bracket, sorry, the Poisson bracket, of a function u with a function u, well, it's going to equal 0. All those partial derivatives cancel out. So that's interesting. That's definitely not the usual algebra. Like if I did x times x, I get x squared. I don't get 0. So that's peculiar. If I've got the Poisson bracket of u with v, and then I reverse the order and do v with u, are these the same? No, they're not. They differ by a minus sign. So again, that's weird. I'll call that antisymmetry. Here's another property. So I've got u and v are scalar functions. What if I now also have a is a real number and b is a real number? Then if I take a times u plus b times v and take the sum of that, so this is the sum of two scalar functions, take the Poisson bracket of that with a third scalar function, w, what is this going to be? Well, it's going to be a. We could pull out the a, because since it's not a function, it's just like a coefficient, we could pull it out. A Poisson bracket of u with w plus b of the Poisson bracket of u, sorry, v with w. This property is linearity. And the normal algebra does obey linearity. Yeah, normal algebra.
A question about linearity.
Oh, okay.
So are we treating a and b as we're treating them as real numbers? So is there any equivalent for real linearity for some kind of function composition in this context, if that makes sense? Or are those just going to be real numbers under the operation of multiplication with the function? Like, is there
real numbers under the operation of multiplication? I think what you're talking about is going to come next. So this is the product rule for Poisson bracket. If we have u multiplied by v, and these are two scalar functions with w, I mean you can define that. So u multiplied v, just the two usual multiplications. But then we could write what this becomes. It's u with v, sorry, u with w, Poisson bracket u with w times v plus u Poisson bracket of v with w. So this is the product rule for a Poisson bracket. Does that answer your question? And you could combine that with what's up above, right? You can combine these properties.
I think it kind of does. Yeah, I was just thinking kind of about, since, this is an operation on functions and you're bringing in real numbers, it seems a little bit odd. But I guess if you're, I guess if you were to express everything in terms of the product rule, that might make more sense. I think that makes sense.
All right. So there's another property, and this is if you've got, suppose we take v with w, Poisson bracket, those are two functions, and then we take that on its own as a function. So now let's take the Poisson bracket of u with this new function. So it's the Poisson bracket of a Poisson bracket. Well, what does this equal? This equals, and this is a bit much to write down, and it's not obvious. It's that minus this. This is non-associativity. Associativity would mean if you just switch the orders around, then you should get the same thing. So if we had an associative situation, then we would just sort of end it there. U with v and w equals u v w, but you just sort of switch the order. But we don't. We pick up this third thing. So the usual algebra is associative, but this is non-associativity. And this formula is sometimes called the Jacobi identity. I guess a way that I like to see it is, right, the first two things, so this equals that would be what you get if it was associative. This term here is a measure of how the Poisson bracket fails to be associative. And the whole thing is the Jacobi identity, not just that last term. So this is called Jacobi identity. So for usual algebra, if I had x times y and z, well, this would be the same as doing x times y and then multiplying that by z. And we'd say, oh yeah, multiplication's associative. We depend on that all the time. The Poisson bracket is not. So here's this is associativity. The other multiplication. All right, so have you seen a Lie algebra before? And the answer is yes. I saw one just the other day. No, this is, yeah, have you seen a Lie algebra before? Does anyone know of a common thing, especially things that we see in mechanics that obeys these properties? Function or operation? No? Well, here it is. You use it a lot. The cross product. So the cross product as an operation on vectors in three-dimensional space, or R3, obeys these properties. So if I have A is in R3 and B is another vector in R3, well, I know that I could define a new vector in R3, A cross B, and that's going to be negative B cross A. I take a cross product of any vector with itself, I get a 0. And I guess the surprising thing might be the Jacobi identity. So all of the properties of the cross product fall into one of these categories. So the cross product in R3 is a Lie algebra, we could say. Jacobi identity for the cross product, it probably has some other name. I forget what it is, but maybe they just call it the Jacobi identity. But that's one that you've seen. So this is very, very mathy here, right? We've just sort of gone into literally abstract algebra to talk about the mathematical properties of this operation, but that's supposed to be part of the beauty of it. Let's take this back to Hamiltonian systems.
Oh, another quick question real quick.
Yeah.
Does the Poisson bracket have an identity element? Does the algebra?
It's not a group. That's what you're asking.
I was just wondering if it had an identity.
I'm going to say no.
Okay.
Yeah. Yeah, I mean, there is another area that we might talk about where we talk about Lie groups. And it's an example of a group. And for groups, you do need an identity, but I think not here. All right. So for Hamiltonian systems, these properties are useful. How so? So if I have a Hamiltonian system, let's say I've got a Hamiltonian function, and I know my system obeys dynamics under this Hamiltonian function, h. It's a function of the phase space. It's a scalar function of the phase space and possibly time. Then from that first property up above, I know that h, Poisson bracket of h with h, has to be 0 because the Poisson bracket of any function with itself is 0. So if my Hamiltonian doesn't depend explicitly on time, or partial h partial t is 0, so that means I've got h is just a function of x, then I automatically know, it just follows directly from the properties of the Poisson bracket, that the Hamiltonian is conserved. So Hamiltonian, let's say energy function is conserved. And this follows directly from a property of the Poisson bracket. And we also have a, this is true not just for h. We knew ahead of time that h was going to be conserved. H is a constant of the motion. But this now gives us a more pleasant way to write any constant of the motion. It's always nice to have a pleasant way to write things, right? So we have a pleasant way to write constants of motion. And it's not just pleasant, it will end up being useful. So they are the time independent functions f of x such that the Poisson bracket, their Poisson bracket with h equals 0. Well, why is that? Well, because from what we wrote up above already, any function f, the way it changes in time is f with h if there's no partial f partial t. So if f with h equals 0, then f is a constant of motion. So that might provide some kind of interesting way to search for constants of motion. Maybe you could construct them somehow. What if we also knew that there's another function, g, that its Poisson bracket with h equals 0? So g is another constant of motion. F, G, I'm running out of letters. I'll use little h. We can define a little h. Little h is a new function, which is the Poisson bracket of f with g. And by this Jacobi identity property, right, let's just go up here. Jacobi identity property. By the Jacobi identity property, f with g, the Poisson bracket, will also have a Poisson bracket that's with capital H that is 0. So if we've got two constants of motion, then we can construct a third. And why is this? This is from the Jacobi identity. If we've got f with h, g, if this equals 0, then, and we'll have some other term that's got g, h, and some other stuff, I don't know. Well, that'll equal 0. Then what do, and we're left with f with g with h. So we just, if you could rewrite the Jacobi identity so you have the sum of 3 terms equals 0. And 2 of those terms equal 0 because one of the elements is 0. Then we're left with this. So from this, this implies little h, which is f with g, is constant of motion. So you could build up constants of motion. Like you could build up a library of constants of motion, just knowing 2, right? Because then we could take h with something else, maybe h with f.
I have a quick question.
Yeah.
Is f plus g not a constant of motion?
F plus g would be, but it's functionally dependent on the 2. So we're thinking of like g could be just some scalar times f, and then yeah, that's trivially another constant of motion. But we're thinking of f and g are like orthogonal in the space of functions. So we've learned something new. If the Poisson bracket of f with g is functionally independent of both f and g, then we've got this actual different function that doesn't depend on the other 2. So yes, it's true that f plus g is, but we don't gain anything from that. We haven't learned a new functionally independent constant of motion.
So then can you just keep doing that and there's infinitely many constants of motion?
I think once you've got f with g, it's possible, yes. If f with g is functionally independent of f and g, then yeah, you could take this new thing and take its Poisson bracket with g, and oh, you've got something new. So you could build up a library. At some point though, in practice, you end up getting a new function that's actually dependent on the others. Like it's a linear combination. Or you'll find that f with g is just, the Poisson bracket is just is 0, or it's a constant value like pi, which is, again, you don't learn anything new because we know that any real number is somehow a constant of the motion. We want things that are functions of phase space and are new functionally independent functions. But yeah, in theory, you could like bootstrap up a whole library of different constants of motion. In fact, infinite numbers. So I think that'll be in another homework. All right. There are some things called the fundamental Poisson brackets, and this is just for canonical systems. Because I did mention before, they're just based on the properties of the Poisson bracket, we could define a new set of systems that are called non-canonical Hamiltonian systems or Poisson systems. But there are, just for completeness, let me mention these things called the fundamental Poisson brackets. And the fundamental Poisson brackets have to do with the Poisson brackets of the Q's and the P's with each other. So Qi with Qj, the Poisson bracket equals 0. Doesn't matter what I or j are. Same for the momenta. Pi with Pj equals 0. And so this is for all I and j. But if you start taking the Poisson bracket of the q's and the p's, so let's say qi with pj, most of these are 0, but some aren't. So this actually equals the, I think this is the Kronecker delta. Kronecker delta. Haven't heard of the Kronecker delta. This equals 1 if I equals j, and it's 0 otherwise. So that means like Q2 with P4 equals 0, but Q4 with P4 equals 1. And that could be useful too. Just you could do some interesting things just based on these fundamental Poisson brackets. That maybe we'll get to later. But I did want to mention, is it 410? Yeah. Non-canonical Hamiltonian systems. I guess if we were to think of the space of all Hamiltonian systems, most of them are non-canonical. And these are sometimes called, maybe put AKA, also known as Poisson. I kind of forget how to write Poisson. Okay, good. Systems. I don't know if everyone in the world calls them Poisson systems. More people will probably know non-canonical Hamiltonian systems. So we can use those mathematical properties of the Poisson bracket to generalize to non-canonical Hamiltonian systems. And here is most of the books on this will just delve into some wild geometric description of things, which maybe you think this is wild already. I don't know, but they usually do it at a level that you need 3 years of differential geometry to know what's going on, and it's not necessary. So the way I start is, let's say I'm just going to define a function. So instead of using u and v, I'm using f and g. Okay, all right. So f and g are just functions of your phase space. Okay, f and g. These are just scalar functions of the phase space. You can define the Poisson bracket as being the gradient of f transpose multiplied by, I'll write this thing, omega x times gradient of g. So it looks like what we had before, where omega x was just the J matrix. We've now defined, so now where omega x is and I guess we have to say what the dimension is. I'm gonna cheat here and give myself some room. How do I give myself a little cheater room? Okay, that's good enough. Oh boy, okay, what did I do? Okay, so X is an n-dimensional phase space. It's not the number of degrees of freedom, it is the dimension of the phase space. Now, omega x is an n by n matrix called the Poisson matrix. And if we were to just write out this thing that I've written in terms of matrices, but write it in terms of components. So this is the sum over ij partial f partial xi omega ij, that's the ijth element of this n by n matrix, and then partial f partial xj. So this is using index notation just to write the same thing as above. So this is for
should that be df d, I mean df dg dxj?
yeah, thank you. So x equals x1 all the way down to xn, and we've got that. So a special case is when omega equals j, that canonical symplectic matrix. And it only works for even dimensional systems. Omega equal j, which would then be 0, the n divided by 2 identity minus identity n divided by 2, 0. So the canonical symplectic matrix, which doesn't depend on x, it's just some constants, it's zeros and ones. But in general, you could have this matrix depend on where you are in phase space. So maybe I'll put that as kind of an aside. We're talking about non-canonical Hamiltonian systems. The non-canonical Hamiltonian equation of motion is, it's defined for any scalar function f over your phase space, f of x. F dot equals the Poisson bracket of f with h for the appropriate h. And in mechanics, h usually comes from energy somehow. So this would be if you were to let f equal just one of the components of the phase space. Let's say you want to know how trajectories evolve. Then say, well, I'll let f equal the ith component of phase space, xi. Then what does this give us? Xi dot equals the Poisson bracket of xi with h. And that would just give us, from that double summation up there, sum from j goes from 1 to n, omega j, j, partial h, partial x, j. We can summarize this equation of motion, noting that if we were to take the gradient of x, remember taking gradient of x with respect to x, this is just giving us the identity. We're in n-dimensional space, so it's the n by n identity. So x dot, all the components change according to this, omega x times gradient h. And then just to remind us, for our canonical system, well, first of all, what is this? This is in general. It's worth saying, in general, this Poisson does depend on x. For a canonical system, omega does not depend on x, right? Omega equals j, and x dot equals, this is what we've written before, x dot equals j gradient h. But this allows us to generalize it. It's usually written this way, not in terms of components of the phase space, but in terms of how any scalar function of the phase space evolves. So this is probably abstract. So to bring it back to mechanics, I will give you an example that we usually don't think of as Hamiltonian. Unless there's any questions up till here.
I do have a question, actually.
Go ahead.
So what happens if omega is the identity matrix?
Omega was the identity matrix?
Yes. Is there any noteworthy aspect of that case? Like, is that a special named case or something?
It wouldn't work. It wouldn't work. Yeah, so for this definition up here has to obey all of those properties of a Poisson bracket. And if you had omega equals the identity, you're not going to obey those. So the Poisson matrix sort of encodes everything that we would expect from the properties of the Poisson bracket. So omega equals the identity wouldn't work.
So omega can't be any matrix. It has to be a matrix that obeys the Poisson bracket properties.
Yes.
Okay.
Yeah. I even put that here. Obeys Poisson bracket properties. Yeah, so that limits like the space of possible omegas. And usually they're not terribly obvious. Some of the work that my PhD advisor did was just sort of in identifying the Poisson bracket for different continuum mechanics PDEs, like the Maxwell-Vlasov for plasma physics and other things for like Navier-Stokes. But the simplest non-canonical Hamilton system is from rigid body mechanics. And it's Euler's rigid body equation. Written in terms of angular momentum. So rigid bodies, if you took intermediate dynamics, you saw me draw like my little box thing that represents a rigid body. So this is a rigid body, like an eraser, which since I'm not on a chalkboard, I don't have one. We got the center of mass, and then the principal axes. So we've got, say, body, these are body fixed directions that correspond to the principal axis frame, B1, B2, B3. And in this body fixed frame, there is a angular momentum vector, H, which can evolve according to how this thing is changing. So little h as a vector, this is the angular momentum. So the angular momentum viewed in the body fixed principal axis frame. Principal axis frame, B1, B2, B3. So I guess just to remind us, this is the principal axis frame. So I didn't want to zoom in. H, the components of H are H1, H2, H3. So H1 is H dotted with B1, etc. So H1 is in the first principal axis direction, H2 is in the second, H3 is in the third. We're just writing the angular momentum. And this is a vector in R3. For rigid bodies, the thing that's important, at least for the rotational equations, and that's what we're talking about, rigid body rotational equations. The mass isn't as important as how the mass is distributed. And the way the mass is distributed, we write in terms of the moment of inertia matrix. So here I is the moment of inertia matrix. And since we're writing this in a principal axis frame, this simplifies to being just a diagonal matrix. And I'll just remind us, this is notation from intermediate dynamics, but B sub P means it's, we're using principal axis as the frame. And everything else is zeros. So we just have diagonal elements. Okay, then usually in intermediate dynamics, we would write Euler's rigid body equations in terms of the angular velocity, but I'm not writing it in angular velocity, I'm writing it in terms of angular momentum. And the Euler's rigid body equations in terms of angular momentum are, I don't know why I keep saying H, the vector H changes in time according to H cross, now we've got I inverse times H. So there's a cross product and that's it. It's nice and compact and pretty. And we usually get this some other way, but I just want, my goal is just to show you this. First of all, what's the dimension of the phase space? The dimension is 3. So we have a 3D phase space. It's the space of all vectors H. So R3. So just by the mere fact that it's odd dimensional, we can't write this in terms of Q dot equals partial H and P dot equals minus partial H, because that's only for even dimensional phase space. Here we have an odd dimensional phase space. So what can we do? Well, so from the, we can define a Poisson bracket, and we can get that from a Poisson matrix. So you'll probably ask me, well, how did you systematically construct that? I don't know. I didn't. I feel like there's a lot of guesswork involved. But let me tell you what the Poisson matrix is, what the Hamiltonian is, and that, hey, this somehow works out to be a Poisson bracket. So let me demonstrate that this set of ODEs is Hamiltonian. It's going to be, it's a non-canonical Hamiltonian. And so we're going to need to find some kind of Poisson bracket and see if the results of that Poisson bracket are the same as this set of 3 ODEs. These are 3 ODEs, right? Because H is a vector. So we can define a Poisson matrix. And here, instead of X, I'm writing H, right? So omega, this Poisson matrix, will be a 3 by 3 matrix that's a function of H1, H2, and H3. Well, I'm going to do this, and it's not obvious why, but I'll define this matrix as H3 minus H2, H1 minus H1, H2 minus H3. This might look familiar as, this is what we wrote as writing the cross product as a matrix. So this is the cross product matrix for H. But right now, just think of it as it's just some random matrix I chose that hopefully has the right properties. So we've defined a Poisson matrix. Now we will define, we need an appropriate Hamiltonian. I guess I'll say the Hamiltonian. Define the Hamiltonian. Hamiltonians are usually physically motivated by energy. We're talking about something, a free rigid body rotating in space. The only energy it has is rotational energy. So we'll define the Hamiltonian as the total rotational kinetic energy. Which we're able to do. So this would be capital H, the Hamiltonian as a function of our phase space is, and you might remember this, this is another way to write the energy. It's angular momentum dotted with angular velocity, but angular velocity is equal to I inverse angular momentum. So just to make that more clear, that's a moment of inertia matrix inverse, which has a particularly simple form. I inverse is just 1 over I1, 1 over I2, 1 over I3 along the diagonal. Okay, so that's the Hamiltonian. If we were to explicitly write it out, since we've got principal axis coordinates, this will look pretty nice. H1 squared I1 plus 1/2 H2 squared over I2 plus 1/2 H3 squared for I3. That seems legit. Okay. Then here's the claim. With this Poisson matrix and this Hamiltonian, this is equivalent to Euler's rigid body equations for any scalar function of the angular momentum, any scalar function f. So maybe just say that then. This for any scalar function f as a function of angular momentum is equivalent to Euler's rigid body equations. Because this Poisson bracket is gradient of f. I guess you got to write it as, you know, the gradient is with respect to the phase space variables, which are h transpose omega h, which is this matrix over here, times gradient of the Hamiltonian with respect to h. If you let f, it's kind of weird, but maybe this is an abuse of notation. Instead of having f be a scalar, if I say f kind of stands in for each of the scalar components, h1, h2, h3, then gradient of h is the identity. So h dot is omega h, gradient of h respect to h. And then what is the gradient of the Hamiltonian with respect to h? It's easier to just see it from this part. It's going to be I inverse h, And this is just H cross product I inverse H. So that is the same as what we have up above. Same. So that's a lot of effort to write Euler's rigid body equations, but it does show that even with this odd dimensional space, somehow Euler's rigid body equations are Hamiltonian once you've defined things appropriately, the right setting. So you view it as a non-canonical Hamiltonian system with the Hamiltonian that's equal to the total rotational kinetic energy. Yeah, the hard part, I think, is this defining of a Poisson matrix. And you can, and maybe I'll leave it as a homework assignment. Maybe it's even in the new one. I don't know. You could verify that this Poisson bracket satisfies all those properties, those 5 properties of the Poisson bracket. A lot of it follows from the fact that we already know that the cross product satisfies those properties of a Poisson bracket, and we've kind of baked that in by rewriting this matrix, the kind of matrix form of a cross product. But you might say, well, what do I gain? Well, we've talked a lot about, when we were talking about canonical Hamiltonian systems, all of the nice properties of canonical Hamiltonian systems, like energy surfaces and geometric things like that. Well, because we've now put the Euler's rigid body equations into that same setting, we can use all of that machinery. So even though the phase space is 3D, but we have constants of motion. We actually have 2 constants of motion. And each constant of motion implies an invariant 2D surface that the dynamics must live on. So the first constant of motion would be the Hamiltonian, so the total rotational energy. And why do we know that's constant? Well, because H with H, the Poisson bracket, is 0. So this implies H, which I'll just write it again, that function, equals constant. That function is a constant. And this formula, this thing equal to a constant, is the formula for an energy, sorry, for an ellipsoid. So in the space H1, H2, H3, this defines an ellipsoid. I'm not the best at drawing ellipsoids, but who is? There we go. So this is a formula for an ellipsoid, and we might call it the energy ellipsoid. So what does this mean? That means the think of our angular momentum vector as it evolves in time, according to this equation. It has to stay along this energy ellipsoid. You can't say anything when I do that. And it has to stay along the energy ellipsoid. So that's one kind of geometric constraint that kind of naturally falls out of this identity or this property of the Jacobi constant. The other surface, I said that there are 2 constants of motion. The other constant of motion is the magnitude of h. It's probably easier if you do the magnitude of h squared. And you could go through the exercise if you want, but you'll find that the magnitude of h Poisson bracket of that, the magnitude of the angular momentum, Poisson bracket with the Hamiltonian, is equal to 0. In fact, any function f that's a magnitude of the angular momentum, just the magnitude, a function of the magnitude, the Poisson bracket of that with h is 0. But this is the easier one to interpret because this implies h1 squared plus h2 squared plus h3 squared equals a constant. Well, this is the formula for a circle. Sorry, a two-sphere. The usual sphere. Maybe I'll draw that in blue. So here's the two. There's the, since that this one's defined by momentum, we could call this the momentum sphere. So that means this vector, the red vector of the angular momentum, has to be where the momentum sphere and the energy ellipsoid intersect. And maybe you've seen this before. I don't know. The angular momentum vector must evolve along the intersection of these two. I guess based on the initial conditions, your initial conditions for H will specify what the energy ellipsoid is and the momentum sphere. And if you just kind of think of it, like where are they going to intersect? It looks like a sphere and an ellipsoid intersect. That's not pretty. A sphere and an ellipsoid intersect in curves, two closed curves. In fact, if I can get this video to show something, maybe we can see it. This kind of gives the idea. Here, this is showing the energy. I don't know why this chooses to show gammas, but here, gamma 1, gamma 2, and gamma 3, these are just the three components of H. So it's H1, H2, and H3. We're showing the momentum sphere and the intersection of the momentum sphere with different sizes of the energy ellipsoid. And this kind of just shows the path that the H vector must travel on. That's kind of showing that this might be an easier way to see it, because you can really see, here's the sphere. It's just kind of, this is a crude figure from like 20 years ago. I didn't make it. But you got the momentum sphere and then the energy ellipsoid, and oh, what do you know? They intersect in a, this is possible trajectory for omega, meaning the angular velocity, but think of it as possible trajectory for the angular momentum is along this side that we can see, and then also on the other side. I think this video also shows something. This is just kind of nicely illustrating a particular case. Here's a case where we've got the momentum sphere and energy ellipsoid intersecting, and that's what the motion looks like in physical space. Here it's using J as the components of angular momentum. Don't know why. And they just sort of taking different values of the size of the sphere compared to the size of the ellipsoid. And I could post this video. I thought it was pretty cool. Let's see, where were we? Yeah, there's that's probably enough for today. I'm not going to start any new topics in 2 minutes, but we'll say some more next time about special things that come along with being a non-canonical Hamiltonian system. There's some constants of motion that actually come from the Poisson bracket. For this particular case, this anything that's a function of the angular momentum magnitude being a constant of motion, you could think of it as arising from how we wrote the Poisson matrix. So because we had a kind of interesting Poisson matrix, that led to a constant of motion. And that's a whole topic called Casimir functions. So Casimir functions are constants of motion that you could think of as arising from the Poisson bracket. And it has to be a non-canonical Hamiltonian system to see this. So they're non-trivial functions for which their Poisson bracket with any other function is 0. Not just the Hamiltonian, but any other function. We'll say more about that. Also, a connection with an interesting topic from differential geometry called Lie derivatives. It's just a kind of generalization of derivatives. Plus you get to write this cool looking thing, the pound symbol, L. But that's it for today.